Assalamu alaikum everyone. So far we have learned the mechanism of the formation of hydrate, and we have talked about the method how to prevent the formation of hydrate, and we talked about what we call the thermodynamic inhibitors, or the addition of thermodynamic inhibitors, or what we call the chemical inhibitors, or how can we prevent the formation of inhibitor using the famous two chemicals, which is the methanol and the glycol. And in today's lecture, we will learn the design procedure or the standard or the guideline how to calculate, for example, the fraction or the amount of inhibitors needed to prevent the formation of the hydrate. So the scenario that I'm describing is this scenario that you have gas flowing in a pipe, for example, and you need to inject in this gas pipeline, you need to inject chemicals such as methanol or glycol, for example, in order to prevent the formation of the hydrate. So we need to calculate how much do I need from this, for example, inhibitors, this chemical inhibitors. So the first method that we're going to apply, or the first approach that we're going to apply, is the fraction of the inhibitors in the aqueous phase, of how much do I have to add as the amount of the inhibitors into that gas stream in order to bind with water, and how much will be the percentage of, or the weight fraction of this inhibitors in the water in the aqueous phase. And the first approach to do that is what we call the Hammerschmidt correlation, where the Hammerschmidt correlation calculate the weight fraction of pure inhibitors in the aqueous phase, which is going to be referred to as Xi. So here, this is what we call as an Xi, which is the weight fraction of the inhibitors such as methanol and glycol in the aqueous phase. So, and you can calculate the value of Xi based on this formula. So, where delta T stands for the desired decrease or desired depression of the hydrate formation temperature, how much will be the decrease in the temperature, and KH is something new that we can call the Hammerschmidt constant of the inhibitors, where the Hammerschmidt constant for the inhibitors can be calculated or can be found. Actually, we cannot calculate it, we can just use it from tables or fixed data or constant data from this table. For example, if you are dealing with ethylene glycol, you can have the KH or diethylene glycol to be 4000, and if you are dealing with methanol, you can use the value of 2335. There are some values that can be also found in the literature, that if you are using triglycol, for example, you can use 5400, and if you are using ethylene glycol, you can use 2700. But as a guideline for this course, we're going to use this values that's listed in the table here. And MW is the molecular weight. So this way you can calculate how much is the percentage or the weight percent of the pure inhibitors in the aqueous phase. The second approach for the calculation is what we call the Nilsson and Bucklin method, where you're going to use to calculate how much methanol can be added in the aqueous phase once the temperature can reach up to as low as, for example, minus 160 Fahrenheit, and you can calculate how much is the delta T, where delta T stands for the decrease in temperature anticipated or resulted from the addition of the chemical inhibitors, and XW is the mole fraction of water in the aqueous phase. This slide is very similar to what we have discussed before as Hammerschmidt method equation, but here I'm going to represent the equation in terms of the decrease in temperature, or in terms of the depression of hydrate formation temperature or hydrate formation point, where again MW stands for the molecular weight of the inhibitors, KH is the inhibitor constant as we have seen before, and yes, and Xi is the mole fraction, or the mass fraction of the inhibitors. And this formula also, if you want to represent the same equation in terms of the mass fraction, which is similar to what we have discussed in the previous slide. Few points to look at when you talk about the design criteria for the or using the design criteria for the calculation of how much of the methanol or glycol, for example, needed as inhibitors, is to know that the fact that once you calculate the injection rate, or once you calculate the mass fraction or the weight fraction of the inhibitors in the aqueous phase, in fact you are calculating how much exactly is the concentration of the inhibitor in the aqueous phase, which means that you can know exactly how much of the water was bounded or was condensed during this process, and how much water is going to be binded to this inhibitors. The second thing is that you need to keep in mind that all these chemicals, such as methanol, specifically methanol and ethanol, might also distribute in other phases, which means that they are volatile, and they can also be found in the vapor phase and in the condensate phase as well, which means that you need to account in your calculation, you need to account for the losses that will take place due to the evaporation, for example, of these chemicals. The third thing is that in the old days they used to find the KH value to be fixed 1297 for most of the inhibitors, but nowadays they found that, or recently they found out that no, this is not very accurate, and the inhibitors type will affect how much is the KH value, and as a result we can calculate, or we can use the value for the KH value as we have seen in the table before, or in the table that we're gonna see in the next slide. Now if your temperature is given in the Celsius, for example, you can use the Hammerschmidt coefficient using this table, or you can use the data or the value used in this table. You can choose, as you can see, there is a slight deviation between one method to another method, and here is like the reported data. For example, GBSA, this is the GBSA book, and this is the Arnold method, for example. This is the Peterson method, but for us to be in the safe side, normally we're gonna deal with the GBSA book, as unless I tell you in the question use some other method. But you have to keep in mind that this value, if you are using the temperature in Celsius, if you are using the temperature in Fahrenheit, you're gonna use the other value, which is 2335 for the methanol and 4000 for the glycols. Some other guidelines for the design criteria of Hammerschmidt equation for the KH value. If you are using, for example, salt, you can use the value of KH to be approximately 2500. If you are using, for example, glycol, you can still use the 1297 value, but in fact, from experience point of view, it was proven several times that this KH value is not appropriate, and therefore the other value of KH can be used, which is the approximately 2000. And normally the design criteria should be go with the lower value of KH, and then optimization should be done based on the data that you are obtained. Or that's why, as we mentioned earlier, thermodynamic approach or the injection of chemical is not always appropriate, and you use it once you utilize all the other solution, and you found out that there will be no other solution except you inject the chemicals. From cost point of view, from optimization point of view, or the difficulty of the process itself, optimizing the process itself is not that easy. It's not that easy task to do. Hammerschmidt equation is also valid for methanol, ethylene glycol, also concentration of 30 weight%, and about 20% for other glycols. And normally Hammerschmidt equation can be also used in the value or in the range. Let me just change the color. And some other resources say that, or recommend that you can use the Hammerschmidt equation for a value, or if the methanol concentration is around 50% and the glycol is around 60 to 70%. So this gives you an idea about how different is the approach or the design criteria from one point to another point, because there are several parameters that may control or may limit the use of these chemicals, and based on the literature and based on the experimental experience, these deviations are still acceptable. As you can see here, as we mentioned here, in general, from theoretical point of view, you can see that the Hammerschmidt equation is valid if the ethylene glycol and methylene glycol concentration is between 30% for methanol and 20% for glycols. But you can still find that people use Hammerschmidt equation, or accepted to use Hammerschmidt equation, if the methanol concentration around 50% and glycols is between 60 to 70%. The second method that looks for the calculation of the percentage, for example, or the percentage of the inhibitors needed to reduce or cause the decrease in the hydrate formation temperature, is what we already explained as Nelson and Buckland equation, where we said that Nelson and Buckland equation use this formula where D represent the decrease or the depression in temperature on the freezing temperature, or in the what we call the hydrate formation temperature, and XH2, which is the mole fraction, if you still remember from the previous slide, XH2 is the mole fraction of water in this case, not the weight fraction. For the Hammerschmidt equation, we use the X to be the weight fraction of the inhibitors in the aqueous phase. For the Nelson-Buckland equation, the X represent, or XH2 represent, the mole fraction of the H2O in the aqueous phase. And here you can use this equation if you're this is very important to know. You can use this equation if the temperature is in Celsius. If the temperature is in Fahrenheit, you're gonna use the equation that you have seen in the previous slides. And the equation can be also readjusted or rearranged to estimate the inhibitor molar concentration as per the following equation, similar to what we have done for the Hammerschmidt equation as well. And then you can calculate how much is the mass fraction of the inhibitors. So the xi, the small xi, this is the mole fraction. Which is obtained from the adjustment of the previous equation. Okay, so this is again mole fraction. You want to convert mole fraction to mass fraction to have a baseline similar to what we have done with the Hammerschmidt. You can use this equation where X capital I will be the mass fraction of the inhibitors. And again, you have to keep in mind that these mole fraction or mass fraction are both in the aqueous phase. One last thing to keep in mind, that this is always good, or this equation is always good as long as you have non-ionic inhibitors. Means that you cannot really use this equation to convert the mole fraction to the mass fraction if you have ionic inhibitors such as NaCl and CaCl2. You're gonna account for the ion concentration in that case, as what we have explained earlier. The third method also used to calculate the thermodynamic inhibitor concentration is what we call the Carroll method, where the Carroll method propose a method based on the activity coefficient, where you're going to introduce something called the activity coefficient, which is gamma, which is again a representation for the concentration. If you still remember from reaction point of view, that the activity coefficient represents the actual concentration of the water. Now you need to calculate the activity coefficient. You use the Margell equation, where Margell equation represent or found the activity coefficient based on the mole fraction of that component, for example. And then you can bring A over RT as a constant. That's going to be known as A, or the Margell equation. In the Margell equation, we're going to call it the Margell coefficient. And then you can simply find the D, which is the depression in temperature, or depression or decrease in what we call the hydrate formation temperature, based on the mole fraction of the inhibitors, and based on a constant which is A over RT, where A capital, which is ART, where A capital is called the Margell equation or Margell coefficient in the equation. So this is Margell equation, and this what we call the Margell coefficient, and the Margell coefficient can be found in the table in the next slide. So this is another method. This is a third method that also built up based on the Nielsen-Bucklin equation. It's very similar to Nielsen-Bucklin equation, if you can see, except that they introduce a new term, which is the activity coefficient. To find the activity coefficient, you need to use Margell equation. Margell equation find the activity coefficient based on constant value, A over RT, and based on the mole fraction of the inhibitors. Then Margell equation, to simplify things, he took the A over T and replaced it with A capital, where A capital is called the Margell coefficient, and this Margell coefficient can be already given in the table that we're gonna represent in the next slide. This is the value for Margell coefficient for methanol, for example. Margell coefficient 0.21. For triethylene glycol, for example, Margell coefficient equal to -15 almost. But you have to keep in mind that this is based in a certain limitation. The limitation will be normally in the concentration. So if you are dealing with concentration of methanol less than 85, we're going to assume that the Margell coefficient will be approximately 0.21. And if you are dealing with concentration less than 50% for triethylene glycol, you're going to use the Margell coefficient to be -15. And as a result, the decrease in temperature will be less than, for example, 94 for the methanol, and less than 20.6 for the case of the triethylene glycol. This is again Carroll method, where you can calculate, for example, how much is the temperature depression or the decrease in temperature of the hydrate formation based on the weight percentage of certain chemicals. Let's say that this curve represent the middle one represent the TEG, this one represent the middle one represent EG, the side one represent TEG, and this one represent, for example, methanol. Let's say that you have 35% methanol. Okay, let me draw, like, let's say that you have a weight percent of 35%. You have, let's imagine this scenario. You have 35% methanol, 35% ethylene glycol, and 35% TEG. And you need to calculate how much is D, or you need to find how much is D. So D will be equal to, therefore, okay, so you have 35 weight percent, so I'm gonna go vertically this way. So in terms of methanol, I will get the decrease in antifreeze, or the decrease of, sorry, not antifreeze, the decrease in hydrate formation temperature will be around 18 approximately degrees Celsius if I add 35 weight percent of methanol. If I have 35 weight percent of EG, this will cause a decrease in temperature, or hydrate formation temperature, approximately 13 or 12.5 almost. And if I'm adding DEG, this means that the value of the EG will be around, let's say, 8, or D will be around 8 degrees Celsius. So this gives you an idea about how do you use Carroll method to predict or estimate, for example, how much would be the decrease in hydrate formation temperature based on the concentration of the inhibitors that you are using. Now, from the previous method, using the 3 methods that you have learned before, you have calculated how much, for example, is the concentration of the inhibitors. Okay. Now you need to calculate how much is the mass of the inhibitors required to be pumped or to be injected in the water phase in the gas stream. So here we are talking about the same concept, but in the previous slides, or in the previous technique, the 3 methods that we have learned, Hammerschmidt method, Buckland method, or Carroll method, will calculate how much is the concentration of the inhibitors needed in the aqueous phase. Now we need to calculate how much is the flow rate, or how much is the mass flow rate, for example, of the inhibitors needed to be injected into the solution. And we can use this equation, where Mi stands for the mass flow rate of the inhibitors, MH2 is the mass flow rate of the liquid water, XR and XL represent the inhibitor concentration. When we talk about XR, means that this is the rich inhibitor mass fraction. When we are talking about XL, we are talking about lean inhibitor mass fraction. And as a rule of thumb, or as a guideline, we can use the XL to be between 60 to 80% for the glycol and 95 to 100% for the methanol. Now the flow rate of the inhibitors calculated from this equation is going to be the amount of the inhibitors needed to decrease the hydrate formation temperature. But in fact, we have to take into consideration the fact that there will be 2 types of losses. The first type of losses will be due to the volatility of the evaporation or volatility of certain chemicals to the vapor phase, such as methanol and glycol. The methanol has higher volatility, so therefore we're gonna calculate for the mass loss, or the loss of methanol that's gonna be to the evaporated to the gaseous phase. And the second type of loss is that there will be some of these chemical inhibitors, such as methanol and glycol, will be soluble in the heavy hydrocarbon, or in the liquid hydrocarbon. So we have also to keep in mind that we need to add this 2 losses, or we need to make up for these 2 losses. So what I'm saying here, that the Mi that we calculated, this is how much methanol, for example, or glycol do I need to add to the system in order to reduce the hydrate formation temperature. But in fact, I need to add extra value, or I need to add certain value for the methanol or glycol to account for the losses that took place through two mechanisms. The first mechanism, that part of the material will be evaporating, especially for methanol. This means that I will lose part of the material in the vapor phase, so I need to make up for that one. The second mechanism, that part of this chemical inhibitors will be soluble in the hydrocarbons, or the heavy hydrocarbon, or the liquid hydrocarbon. Therefore, I'm going to lose that part also of the heavy hydrocarbon. Therefore, I need to make up for these 2 values. So in addition to the Mi, I have to add 2 other values that I'm going to calculate it later on, or see how do I calculate them, and based on that two values I will get the final answer for how much is the inhibitor that's needed. So this MI excluding the fact that you have losses. So this MI is not the final one. This MI is just the amount of methanol needed to reduce the temperature if there is no losses. With the losses, you need to add these two values that we're going to learn how to calculate it from the next two slides as well. Now, inhibitor losses in hydrocarbon phase will be very small for the glycol, but will be very significant for them in case of methanol. And it's very similar to the fact that very similar to the vapor phase losses as well. If you are using methanol, you will have high loss of material to the vapor phase. Now, for the losses in vapor phase, as we explained earlier, that methanol and ethanol, specifically methanol, which is like chemical inhibitors, will evaporate because it's highly volatile. It will evaporate in the gaseous phase. And the glycol also will evaporate, but not similar to the methanol. Methanol will evaporate at a much higher rate than the glycol. Therefore, the losses of the methanol in the vapor phase will be very high. Therefore, we need to adjust this in order to account for how much, because once you add, so this is what I'm explaining, what we are talking about. Here is the gas stream. So once you add methanol to it, part of the methanol will be volatile and will be lost into the vapor phase because methanol is very volatile, and therefore there will be certain material, certain amount of methanol that's going to be lost to the vapor phase, and we need to calculate, or we need to take this into consideration. That's why we need to adapt this chart that you can see here. And this chart will give you an idea about how much will be the loss of methanol, for example, in the vapor phase in the unit of pound per million standard cubic foot of the gas divided by methanol in water phase as weight percent. And if you know how much is the operating pressure and the temperature, but you have to keep in mind that here the temperature represents what we call the lowest temperature in the hydrate inhibition system, which means that the new hydrate, which is the new hydrate formation temperature. So I'm going to use this chart. If I have two pieces of information at least, I need how much is the pressure. Let's say I have 1000 pressure psi, for example. Okay, and I need to calculate how much is the new hydrate formation temperature. Let's say that the new hydrate formation temperature will be 55 Fahrenheit. This means that I can find simply how much of the methanol will be lost, approximately 1.6 of methanol in vapor phase in the unit of pound mass per standard meter cube, standard cubic foot of the gas divided by the methanol and water phase percent. And then we're gonna do certain calculation in order to calculate how much exactly of methanol has been lost already to the gaseous phase. And we will see toward the end of this chapter, we'll see one example that show the whole details of how to use this chart. Again, the same interpretation for the chart that we have dealt with before, that talk about the loss of methanol in the vapor phase, and how to calculate for, or how to accommodate, or to calculate for the losses that's going to take place from the evaporation of methanol. But in this time we are using the standard unit system, where the pressure will be in kilopascal in the y-axis, and in the x-axis you have the kilogram of methanol per standard million meter cube of the gas, divided by the mass percentage of methanol in water phase, in the liquid phase. And as we explained earlier, this is like good for methanol only, because glycol is assumed to be less volatile than methanol, so we don't need to calculate for the losses of that compound, which is the glycol. Now in this slide we're going to learn how to calculate for the loss of the inhibitors to the liquid hydrocarbons, which is the scenario that's highly expected, that when you inject the chemicals, you have also with the gas, you have certain material in the liquid phase or in the hydrocarbon phase, which is like hydrocarbon material, and part of this material, part of the inhibitors such as methanol or glycol, will be lost due to the solubility of these chemicals in the liquid hydrocarbon. So we need to learn how to calculate this one. Now we will start with the easy one. The easiest one is the glycol. We said that for the glycol or the ethylene glycol, the loss in general is very small or very little. This means that we don't need any chart, any specific chart. So we can simply say this rule, that for example for glycol, specifically ethylene glycol, you can take the loss to be approximately 40 gram of a glycol per 1 meter cube of the NGL or natural gas liquid. hydrocarbons in general. So therefore this is very little quantity. So for ethylene glycol, for example, for glycol in general, we can simply say that for ethylene glycol, as a rule of thumb, we can take it to be very small, and we can consider it or assume it to be 40 gram per meter cube of the natural gas liquid. Now the more complicated scenario is for methanol, because methanol solubility in naphthenic hydrocarbons is less than in paraffinic hydrocarbons, and in aromatic hydrocarbons is 4 to 6 times higher than the paraffin. So methanol has certain solubility, or the solubility of methanol deviate based on the type of the hydrocarbons that you are dealing with. So if you are dealing with aromatic, the solubility aromatic hydrocarbon, the solubility of the methanol will be very high. If you are dealing with paraffinic, the solubility of methanol will be mild. If you are dealing with naphthenic, for example, the solubility of methanol in naphthenic material or naphthenic hydrocarbon will be much less than the paraffinic, and the paraffinic will be less than the aromatic. So this is the sequence. The aromatic will be the highest, then the paraffinic, then the naphthenic. Therefore, we need to look at these deviation in order to develop how can we calculate the amount of material or the amount of methanol, for example, loss in the liquid hydrocarbon. And therefore, we're going to use this chart, where this chart is based on experimental data. And as you can see in this chart, you have in the x-axis you have the temperature, in the y-axis you have the mole percentage of methanol in the hydrocarbon phase, and here you have the mass fraction, or what we call the percentage of the methanol, for example, or the mass fraction of methanol. And we're going to see how to use this chart later on in more details. Okay. But for simplicity, let's look at this scenario here. For example, assume that I have a temperature of 10 degrees Celsius. Let's say that I have a system that I have 10 degrees Celsius, and I know that I'm gonna inject methanol, and the methanol has a concentration of 70%. So I'm gonna go and dig where is the 70% methanol, for example here, 70% mass of methanol. So I'm gonna go this way vertically till I hit the 70% weight of methanol, and then I can calculate the mole percent of methanol in the hydrocarbon to be equal to 1 approximately. So for each 1 mole, for example, of the hydrocarbons, I will have 1 mole of the methanol dissolved in that material. If I'm using a concentration or an inhibitors that has a concentration of methanol approximately 70%. But you have to keep in mind always that this chart again are based on experimental data. And one more thing, on one important thing to look, that sometimes the physical losses of the hydrocarbon of the inhibitors might contribute to much less than the volatilization or the solubility in liquid hydrocarbon.